Good morning, everyone. Welcome back to 098. We are going to continue looking at our Unit 1 notes. So we have finished working with fractions, reducing operations on fractions, that sort of thing. So you're able to complete your Lumen homework pertaining to that particular section. So you should be looking at 1.1 and 1.3 assignments. I sent those via email, just clarifying those are the ones you want to look at. They're called practice. The real number system. Okay, perfect. So what I want you all to think about is what it was like, or what it's like for little kids, little tiny chiquitito kids who learn how to count for the very first time. I would imagine that you would agree with the fact that they start to count in terms of like 1 item, 2 items, 3 items. So they begin with 1, 2, 3, etc., right? You can picture a sibling or a relative or anything like that who's just starting to learn how to count. So in this very small circle in the center here, I want you to write down something called the natural, or in other words, counting numbers. Okay, that's essentially where we begin, right? The natural or the counting numbers. And when we say natural or counting numbers, we're referring to starting at 1 and then progressing forward. At some point, kids start to learn what it means to, let's say they have one utensil in front of them and then suddenly you take that utensil away. So they no longer have that utensil with them. So essentially they start to learn the value of 0, what the number 0 refers to. So once we had our natural counting numbers, we expanded that to include 0. By including the number 0, we're now referring to the whole numbers. So consider the whole numbers takes into account all of these natural counting numbers, but it also includes 0. So let's take this idea a step further. Let's say that kid who's learning how to count, learns about 0, what that means. Let's say that kid gets older and starts to have some sort of allowance or whatever. And then let's say they lend a couple bucks to a friend or a classmate or a relative. Then the concept of owing comes into play, right? So you owe me $2. You owe me $5. So instead of being a positive value, it's actually a negative value, that concept of owing. So we can now introduce integers. I really want you to commit to memory what integers are, because this is something you will see again and again and again throughout our course. You'll have several word problems that will ask for integer answers. And if you're responding with a decimal or things like that, then you don't understand what integers actually are. So think of integers as that idea of owing, the negative numbers. So we can actually describe integers as basically all of the values, all of the whole numbers that you can think of, and their opposites. So from negative infinity, essentially, -3, -2, -1, 0, and then towards positive infinity. Hopefully that's clear. I want you to also consider that integers, negative infinity, -3, -2, -1, 0, 1, 2, 3 to positive infinity, notice that the integers does not take into account decimals. It does not take into account fractions that don't result in whole numbers. So integers are, by definition, whole numbers, right? And their opposites, which is why I've included the negatives. Well, now that we've talked about integers, whole numbers, and their opposites, well, what about those decimals. That's when we branch out a little bit more and we say, okay, well, let's think of a bigger number system. Well, let's think of something that is larger, that encompasses more than just integers. And we define that or describe that as our set of rational numbers. So rational numbers includes integers, whole numbers, counting numbers. That's why it's all encompassing here. But we have to take it a step further. So when we describe rational numbers, we also have to include terminating decimals, terminating meaning ending, right? Not repeating. So a terminating decimal ends. So an example of that could be 5.361, right? That is a perfect example of a terminating decimal. Another example could be a fraction. Let's say we had, I don't know, something simple, 1/5. If you had 1/5 and you said, okay, well, when I punch that into the calculator, that gives me 0.2. So it results in a terminating decimal as well. So I hope that's clear in terms of terminating ending decimal. The other type of rational number beyond all of the integers is a repeating decimal. Okay, so repeating decimals are also rational. An example of that might be 7.33333 repeating, right? It's rational. It repeats. We can kind of see that it makes sense. Think of rational like a person. Sometimes it's helpful to think that way. Or another example, based on what we've learned in a previous class, is something like, I don't know, 21/99. We already learned that when you have a fraction, 21/99, this actually refers to the repeating decimal, 0.212121, etc. Okay, how cool is that? So when you think of rational numbers, I want you to think of rational meaning it could be terminating decimal, it can be a repeating decimal, it can be an integer, it can be a whole number, it can be a natural counting number. So rational numbers encompasses all of these definitions. Now over here on the side, we have another bubble that we're including in the real number system. So if we have a set of rational numbers, we also will have a set of irrational numbers. Irrational numbers. One of the most famous irrational numbers is pi. If you take your calculators and let's say you're going to punch in pi, I'm going to press the pi key and then I'm going to press equals. I've got 3.141592654. Whoa, what's the next number going to be? It doesn't end here. We know that pi does not end here. It doesn't repeat. It's not terminating, so it must be irrational. So I'm going to write here that pi is 3.1415926 ... meaning it continues on and on. So we can make a note that it would be easy to identify an irrational number because they do not terminate nor repeat. Okay, it's easy to identify whether or not we have an irrational number because they do not terminate and they do not repeat. Hopefully that's clear. And that's our little spiel of the number system. I'm going to put a couple stars next to integers because I really, really want you to be familiar with that terminology. I want you to be comfortable with the fact that if we're referring to an integer, we know that it's going to be a whole number or its opposite, meaning the negative. Okay, negative whole numbers. Good. All right, let's continue on with our notes. Page 6. Let's talk about inequalities. So the following is a list of inequality symbols that you should be familiar with. We have less than. Oftentimes, these symbols will trip people up. Think of this as an L. Isn't that an L, right? Right? This is like an L. Think of sign language. So L, less than. So if it's not an L, it's got to be the greater than. So we have less than, greater than, less than or equal to, greater than or equal to, and then we obviously have not equal to. Hopefully that is clear. Okay? I want you to note this statement here. This says y is less than 4. But I also want you to consider this statement here. 4 is greater than y. Now, I want you to recognize that these actually say the exact same thing. They're just backwards. So y is less than 4 implies 3, 2, 1, 0. It actually could also imply 3.1, 3.2, 3.3, right? Because that's smaller than 4. 4 is greater than y. Says the same thing. So I want you to be comfortable first reading those kinds of solutions and then being able to be critical about what those values are. Right? Think logically about what those values are. Good. I want you to have that in your back pocket for when we actually see inequalities later in the semester. But we're going to look at just a few. So, true or false? Please determine if each statement is true or false. I'm going to give you all 60 seconds. I would like you to look at statements 1, 2, and 3, and then tell me, what do you think? Are these statements true or false? And do that for each one. 60 seconds starting now. Okay, we have a ton of answers coming in. Let's take a look and see what we think here. Okay, so first off, we have -2 is greater than or equal to -8. Now, when you think of this, it may be helpful to consider a number line, right? So let's go ahead and just draw a number line real quick. I'm going to put 0 over here, right? 0 doesn't have to be in the very center of my number line. You can always shift it over if that's helpful. So I'm shifting over the number line, and now I'm going to write in my negative values. So we have -1, -2, -3, -8, correct? Now, I want you to consider the further right we go, the greater we get. The further left we go, the smaller we get, right? The lesser, I would say. So just by looking at this particular number line, when we say that -2 is greater than or equal to -8, we are definitely going to say true. So very nice. Very nice. Now let's take a look at number 2. -7 is less than or equal to -7. Now, I'm sure there could be, awesome, Ciasia. I would imagine that there might be the thought process here that says, wait a second, -7 is not less than -7. It is equal to. So what does that mean? Well, think of the word or. When you see less than or equal to, greater than or equal to, that word or implies that as long as one of the conditions are satisfied or is satisfied, then it is in fact a true statement. So because -7 is equal to -7, this is actually also true. That or implies that one or the other has to be true. So sure, -7 is not less than -7, but it is equal. So it is a true statement, as crazy as that might sound. And then number 3, -9 is greater than -9? No, absolutely not. In order to be a true statement, it should say -9 is greater than or equal to -9. And Kayla, that's exactly why I wanted to put this out there, so that we can kind of explore the terminology behind it. That word or is so powerful. So I'm glad that it was meaningful. Next, I briefly wanted to touch base on the absolute value. Oftentimes in class, and I'm just thinking back to the 13 years that I've been at MCC, how crazy is that? Whenever I ask students to define absolute value, 9 times out of 10, no one gives me a definition. But when I say, let's skip the definition for a moment and try some problems, you all have no issue with this. So, for instance, Kevin actually already commented on the absolute value of -3. Kevin said the absolute value on -3 is 3. I totally agree. He is correct. What is the absolute value of 22? Well, 22. What is the negative absolute value of 7? Now I'm going to hold off on that for a moment. Noticing these two here, the absolute value of -3 is 3, the absolute value of 22 is 22, it would help us if we figure out what the heck we're actually talking about. What is absolute value? So absolute value, how we are going to describe it for our notes, is the distance from the number to 0. The distance from the number to 0. Now I want to throw something out there to you. Notice the word distance in the definition, the distance from the number to 0. So let's say that you and I were having a conversation and I said to you, you know what, I'm feeling pumped. Later today, I'm going to go run -5 miles. What might that look like? Doesn't that sound really, really strange? And wouldn't that be a statement I would probably never say other than to provide a very weird and strange and uncomfortable example? So if I told you I'm going to run -5 miles, you would be like, what does that look like? What are you saying here? What are you talking about? So the idea is that when we refer to distance, we're talking about positive values. We're not going to describe distance as a negative because we don't. The only time we describe distance or length as negative, Patrick, running backwards, yeah, that would be really, really weird. We could describe below sea level, right? Negative, 200 meters below sea level, that kind of thing. But typically when we talk about distance, we talk about positive numbers, a positive distance. I'm not going to go run -5 miles. That's just really, really weird. So going back to our notes, the absolute value of -3 is 3 units from 0. The absolute value of 22, the number 22 is 22 units from 0. Do you see that distance? So number 3, Kayla, you had mentioned that number 3 is actually going to be a -7, and I could not agree more. So Kayla, I'm going to try and read your mind from a distance, right? And Kayla, I'm going to say that you looked at this absolute value of 7, and you said, well, the absolute value of 7 is 7. But then you said, well, there's a negative sign in front, and you can't just pretend it's not there. So you bring that down, and you say your answer is a -7. I hope you would agree with me on that. And I would imagine that any of you who are kind of thinking about this, you might say, well, order of operations, what does that mean? Does that mean you take care of what's in the absolute value symbol first, or the absolute value sign first? And yes, you do. So keeping that idea in mind, take a look at number 4. Excellent, Kayla. See, I'm a mind reader sometimes. I love it, even from afar. So for number 4, we have the negative absolute value of -15. Type in the chat what you think this value becomes when we simplify. Negative absolute value of -15. What are your thoughts? Thinking back to the concept of, and thank you, Rachel, thinking back to the concept of order of operations, and we're actually going to dive really deep into order of operations in just a little bit. I want you to consider what we must do first. This says a negative absolute value of -15. Now the absolute value bars take precedence of before multiplication. So I want you to think of this idea, PEMDAS, the order of operations. The P in PEMDAS refers to parentheses, and absolute value bars are a very special parentheses because they have their own attribute. So believe it or not, the first thing you're going to have to do is this. you're going to have to say, well, self, what is the absolute value of negative 15? If you say, okay, well, the absolute value of negative 15 is a positive 15, well, guess what? Now you have to bring down the negative in front. So your answer should actually be negative 15. Another way to look at this is going to be a little strange, but I'll write it anyways, is essentially saying because this is a negative absolute value of negative 15, would you agree that this is kind of saying negative 1 times the absolute value of negative 15? These two statements are equivalent. These two expressions are completely equivalent. No, that's okay. Don't feel bad about this. That's why I want to dissect it together. So notice here, the absolute value of negative 15 is in fact 15, but we still have to multiply it by the negative 1. P, M. Notice the location. We had to take care of parentheses before we even get to multiplication. So we simplify and we find that it is in fact negative 15. So I hope that was super clear in that regard. Very cool. Very nice. I love this. Our next topic is on addition and subtraction of real numbers. So we want to get into some terminology that I think is super, super important for you all. Now, we have something called opposites. When we're talking about addition and subtraction of real numbers, we have something called opposites. Another phrase that means the same thing as opposites is called additive inverse. Okay? Opposites, or let's make this plural, additive inverses. Okay? Additive inverses and opposites. I want you to kind of say those because I want you to be comfortable with using that kind of terminology as you describe the relationship between numbers when you're adding or subtracting. Okay? So opposites or additive inverses. So for example, negative 3 and 3 are opposites. We know this because negative 3 plus 3 results in 0. Interesting, right? So opposites essentially cancel each other out. That's going to be really important. Opposites cancel each other out. That's why I left the little point of information on the side here in this cool box. So let's fill in the blank. Additive inverses or opposites cancel each other out. And it leaves you with a 0, right? Think about adding or subtracting and leaving you with a 0. Okay, so we're just going to name a few other pairs of opposites. So I'm going to start with integers, right? So instead of negative 3 and 3, let's use, I don't know, negative 7 plus 7 is equal to 0, which implies that negative 7 and a positive 7 are opposites. But what about if we want to talk about fractions? Because we're not just dealing with integers. We can deal with any type of rational number. So what if I said 1/2? Do you agree that the opposite of a positive 1/2 is a negative 1/2? Good. Well, if that's the case, then 1/2 plus a negative 1/2 will result in a 0. You give me half, and then you take it away, and you leave me with nada, okay? So a positive 1/2 plus a negative 1/2 equals 0. Another example, we can use decimals. So let's say we had 0.36. The opposite of a positive 0.36 is going to be a negative 0.36. Typically, I don't write these signs back to back using a plus and then parentheses surrounding the negative. I will simply simplify those signs, but we'll get to that in just a little bit, okay? These are just examples of different types of pairs of opposites so that you know what it would look like for two terms to cancel each other out with addition and subtraction. They have to be opposite signs in order to cancel each other out. But notice they're the same quantity. Cool. Very nice. Multiplication and division of real numbers. So we have something called the reciprocal. Now, there's a synonym to this, another phrase that means the same thing as reciprocal, and that is multiplicative inverse. Okay? You should say that. I wish I can hear you all say that. Can you all say that? Multiplicative inverse. Doesn't that sound nice? It just rolls right off the tongue. It's so nice. Multiplicative inverse. Multiplicative inverse. It's nice. I like it. So let's say that we have negative 4/5 and a negative 5/4. Believe it or not, notice they're the same fraction, just flipped. Also notice they have the same sign. In order for two numbers to be reciprocals of each other, they have to have the same sign, right? And then they're going to be the exact same value, but flipped. So negative 4/5 times negative 5/4 is in fact a positive 1. So just like with opposites and additive inverses, they cancel each other out, but it leaves you with 0. When we talk about multiplication, when they cancel each other out, it actually leaves you with a 1, right? Think about something basic like 10 divided by 10. 10 divided by 10 is 1, right? But 10 divided by 10 is actually the same as 10 times 1/10. Reciprocals. You see? So let's fill in the blank here. Blank or reciprocals cancel each other out, leaving you with 1. So that's going to be multiplicative inverses. Multiplicative. For those of you who said it out loud, doesn't it sound nice? It just sounds so nice. I love it. Multiplicative inverses or reciprocals cancel each other out, leaving you with 1. Yes, exactly. Exactly, Kayla. So it's applying that concept of how would you cancel the expression out using multiplication or division. And essentially, we're noting that the reciprocals will cancel each other out, leaving you with 1. So just to name some other examples of reciprocals, let's say I start again with that negative 7, right? I have a negative 7. Now I have to think reciprocal. We're not thinking opposite. We're thinking reciprocal. So the reciprocal of a negative 7 is going to be a negative, and remember, we flip it. So if we have to flip this, that's going to give us negative 1/7. And that leaves us with a positive 1. So negative 7 and negative 1/7 equal 1 because they cancel each other out. Another example of pairs of reciprocals, if I write 2/3, you can tell me the reciprocal of that. And then for number 3, if I write negative 6/7, let's do negative 6/11, you can write out the reciprocal of that one. So just take a moment, fill that into your notes. Fill those two into your notes. And you should be getting that the reciprocal, yes, Claire. Notice here that we have the whole number negative 7. You asked if it relates only to fractions. Isn't every whole number capable of being written as a fraction? Think about this in negative 7, our integer. We can write this over a 1. So the reciprocal of a negative 7/1 has to be negative 1/7. So really, we can apply this to all of our rational numbers. Okay, so we have 2/3 times the reciprocal of 2/3 is 3/2. That's what's going to give us a positive 1. If we accidentally changed the sign here, then a 2/3 times a negative 3/2 would be a negative 1, and that would be a problem. We simply want them to cancel, leaving you with a positive 1. Similarly, with number 3, we have negative 6/11, so the reciprocal is going to be a negative 11/6, because when those cancel, you'll be left with a positive 1. All right? Beautiful. So now let's move into a few examples where we're essentially just looking at operations of real numbers. Okay, I would like you to consider that when you are multiplying or dividing values, a negative times a negative is a positive, right? A positive times a positive is a positive. So essentially what that means is when you have a pair of the same signs, it results in a positive value. If you have a negative times a positive, negative, and if there's a positive times a negative, still negative. So you need a pair of those signs to result in a positive, okay? So I want you to think about that as you work through these problems. Okay, so for number 1, we have -3/7 times -2/9 times 14/6 times -1/5. What I would like you to do is just take 60 seconds to practice what we learned at the very beginning of these notes, where we multiplied fractions. And I also want you to be careful with your sign. Think about the resulting sign after you multiply everything. 60 seconds starting now. I'm going to simplify number 1 how I would do it. It doesn't mean you have to do it this way. There are multiple paths towards the same destination, right? Okay, so we have -3/7 times -2/9 times 14/6 times -1/5. I personally note here that 7 and 14 can be reduced, right? Numerator for denominator. So I'm going to say here that the 7 divides into 7 once and 7 goes into 14 twice. It's just my personal preference. I feel like why not start there? Notice here I have a 3 and a 9, so 3 goes into itself once and into 9 3 times. Lastly, I see we have a 2 and a 6. I could also reduce this 2 and this 6, but I'm just going to reduce across fractions because I'm just, personal preference. So 2 divides into 2 once and 2 divides into 6 3 times. Okay, let me rewrite. So now I have -1/1 times a -1/3 times 2/3 times a -1/5. So at this point, I want to notice numerator for denominator that we actually can't reduce anywhere else. So I'm simply going to move from left to right. -1 times a -1, +1, times 2, +2, times a -1, -2. And then 1 times 3, 3, times 3 is 9, times 5 is 45. So when you said -2/45, you were totally correct. Notice the process that I took. I reduced everything up front, and then I simply moved from left to right. Always move from left to right when you multiply fractions. Because we reduced everything up front, we know that our final answer is going to be perfectly reduced as well. Now, for number 2, the real idea that I wanted you to get comfortable with for number 2 is simply assessing this and moving from left to right. So we can take our tool and we could say 27 minus 42. We know that when we have a smaller number subtracted by a larger number, we're going to be in the hole, right? We're going to be essentially in debt. So we know that's a -15. Then I'm going to add 121. That means we're going to be up quite a bit. So positive 106. Then I'm going to subtract 11, which means we decrease just a tiny bit, so we're at 95, and then I'm going to subtract 19. And that leaves me with an answer of 76. Beautiful. Notice here that we simply moved from left to right. I urge you to do exactly the same thing. When we have the conversation about the order operations, I'm going to keep harping on that. Move from left to right, but be very critical. For number 3, we have division of fractions. We learned that when we are dividing fractions, we must keep the first fraction and multiply by the reciprocal of the second fraction. So first, we rewrite 11/25 times the reciprocal, -35/44. At this point, once we have rewritten our expression so that we can actually perform operations, then we're good. So meaning that we can actually reduce. So 25 and 35, I'm going to divide both by a 5. I see that that's a common factor. 5 goes into 25 5 times. 5 goes into 35 7 times. Next, I notice my 11 and 44. I see that I can divide 11 into both of these. So 11 into 11 is 1, and 11 into 44 is 4. At this point, if we were to simply rewrite so that we can see this nice and clearly, we have 1/5 times a -7/4. Notice nothing else reduces, so we simply move from left to right. 1 times a -7 is a -7, and 5 times 4 is 20. So Kayla, excellent job on answering all three of those. So we had -2/45 for number 1, 76 for number 2, and -7/20 for number 3. As always, please don't hesitate to ask questions in the chat, but let's continue. There's a note here that I want you to consider, and I really, really, really don't want you to forget this. You're welcome, Kayla. 0 divided by a number, or in other words, written as a fraction, 0 over a number, will always be 0. And I can prove that to you just by showing you in my calculator. So let's take 0 and let's divide it by, I don't know, 8. So 0 divided by 8, 0, correct? But notice here that when you flip the order and you say the number divided by 0, or in other words, number over 0, is going to actually be undefined. So let's take that same 8 and instead divide by 0. So 8 is the numerator, 0 is the denominator. Look what your calculator gives you. When you're taking, a test or you're completing a homework assignment and you're dividing by 0, you're not going to say error. You're not going to have a question that says 15 divided by 0 and your answer be error. Please don't write error. Okay? You need to use the word undefined. That's what we're referring to. There is no definition for that. It doesn't exist at that point. So a number divided by 0, undefined, that'll be the terminology. If you write error, I will laugh for sure. I will probably give you the credit anyways. Really, it should be undefined. Okay? Excellent. Let's turn the page. Now we are ready to talk about the order of operations. So let me raise this up just a tiny bit so that we have this in full view. The order of operations. So we're going to start off with P. P in this case refers to parentheses. I swear, I feel like I heard all of your thoughts all at once. Resounding parentheses. Now, when you think of parentheses, I want you to consider all the different types, okay? So the first type that we're all familiar with is actual parentheses, right? Parentheses can house information, so we know that we would start with looking at what's inside the set of parentheses. Okay, cool. But what about these? Brackets. Don't brackets house information as well? Certainly, you've all seen this before. You can have an expression inside the brackets that says something like 5 minus 3. You would take care of the 5 minus 3 first. So brackets can house information. What about these? These are called braces, okay, like braces on your teeth. I know we are used to calling them squigglies or curly bars or something like that. No, please, please, please call them braces. These are a set of braces. Typically, they're used to denote a set. But we could also use them as a type of parentheses that house information that you have to take care of first. So braces is another type of parentheses. What about one we saw already? Absolute value bars. So we saw the absolute value in problem numbers 3 and 4, right? For number 3, we took care of the absolute value of 7 first before we brought the negative down. For number 4, we took care of the absolute value of -15 before we brought the negative down. So we actually had to apply that concept of PEMDAS even though we had absolute value bars. So essentially, it's another form of parentheses. It's something that houses information. The last one that I want you to consider, which might, kind of throw you off a little bit and be like, whoa, for real, is a radical. So for instance, the square root of a number. It could be a square root, cube root, fourth root, whatever. We're essentially taking the nth root of an expression. So for instance, as an example, I can have the square root of, let's say we're going to do, I don't know, 12 minus 8, right? You wouldn't say, let's take the square root of 12 and then minus the square root of 8. No, it's housing information. You would say, well, I'm going to do 12 minus 8 first, because then that's going to give me the square root of 4. And then for those of you who are familiar with square roots, you're going to say, and that's just 2, right? That's how you would evaluate. This is how you would simplify. So I want you to keep that in mind, that all of these represent types of parentheses. You'll have to work from the innermost set of parentheses outwards. So let's write that down here. We must always work from the innermost set of parentheses outwards. So we're going to work from the innermost set of parentheses outwards. That's kind of like the direction that we are going to go. That concept can be a little bit tricky. I think one of the things that I want you to keep in mind when you're looking at an expression, and let's say it has a parentheses and parentheses and parentheses, right? Like they're just embedded parentheses. You want to work from the innermost set of parentheses, evaluate, and then move outwards. The other thing that trips us up is the whole idea that when you are looking at sets of parentheses, when you're focused on the innermost set of parentheses, you have to take care of the expression inside that set of parentheses, which implies the operations have their own order, PEMDAS, right? So for instance, you want to multiply and divide before you want to add or subtract. And if you had an expression in the parentheses that involved multiplication and addition, for instance, you would have to multiply before you add. Every time you look at a set of parentheses, you reevaluate and you say, what is the order in this set of parentheses? That's how you evaluate, okay? Yes, Alexis, you're correct. In terms of the order, you want to move from left to right. We're going to have a deeper discussion about what it looks like when you have multiplication and division back to back and what comes first, and then same thing with addition and subtraction. But yes, you also want to think about moving from left to right, okay? Or in this case, you're looking at me, left to right. All right, anyways, that is it for today. Continue to work through your material in Lumen. I would say don't move on to the order of operations homework until we finish our notes tomorrow. Tomorrow, we will finish Unit 1. Excellent job. That was fantastic. Enjoy the rest of your day. Bye, everyone.